Okay, so good morning. I'm going to be talking about a temporal resolution study for the flow past the cylinder simulations. Now, as a little bit of background, if you're not familiar with the flow past the cylinder simulations, what happens is there's flow going past the cylinder that creates a vortex shedding pattern in the wake of the cylinder. So this cylinder could represent a chimney in the real world, or a mooring cable in the ocean. So it could have lots of applications. And what people are mostly worried about is if this flow going past the cylinder creates these vortices could lead to vortex-induced vibration, which could vibrate the cylinder, whether if it's a chimney, or it could be a mooring line. So the main non-dimensional number that people use is the Struhal number, which is this ST right here, and it has the frequency of vortex shedding times the diameter divided by the velocity, the free stream velocity. So for the temporal resolution study that we're looking at, so if we guess the Struhal a little bit higher than what it actually might be, then we can get a guess for the frequency. And from that, 1 over the shedding frequency is going to be the shedding period. And then if we say we're going to take 10 samples per shedding period, then we get our delta t. That delta t is used for our time step. So we're going to say we're going to probe the solution every 10 times for every shedding period. So that's how we get our delta t. And then we say nn is going to be 100. So we're going to take 100 samples. So we say the final time is going to be nn times delta t. So that means we get 100 samples. And because there's a transient solution in the beginning where the solution hasn't reached a stable solution, we're also going to have a second time step, which is going to be twice as large as our time step where we're looking at a portion of the solution that's of interest. So we'll use our delta t later on in COMSOL, I'll show you. But we also have a problem where the flow coming towards the cylinder in COMSOL, it has a ramp up time. So it doesn't immediately have the same uniform velocity throughout the whole domain. What happens is there's a ramp up time of 0.25 seconds for the flow to develop to its maximum velocity. And then for the flow to reach the back of the domain, it takes another set amount of time, which is the width of the domain divided by the velocity. So these two time quantities added together is when we start collecting our samples. So that's the start time. Now, I have a little animation saying that a little bit further in time, the uniform flow gets to this position, and then later on it gets to this position. And that's how I'm saying that the flow is getting developed, and it takes time for the free stream velocity to be uniform throughout the computational domain. And that time, again, is W over U. Okay. So I'm going to end the PowerPoint. Now we're going to open up COMSOL. So it loaded. So now we're going to go to Model Wizard, 2D, and we're going to go for laminar. Add. Now go to Study, Time Dependent, hit Done. All right, so we're going to define our parameters. Say geometry here. Diameter is 0.1 meters. Width is 25 times the diameter. Height is 17 times the diameter. Now, what else are we looking at? CX, which is the position of the inlet, it's going to be 5 times the diameter. And let's keep going here. Parameters. Say flow. So flow, we're going to say Reynolds of 100. We're going to say the density is 1,000 kilograms per meter cubed. Viscosity is 1 e to the minus 3. Pascal seconds. Now the free stream velocity is going to be the Reynolds and the viscosity divided by the density times the diameter. All right. Next, we're going to do the time step. Just like we did in the PowerPoint, we guess this through all at 0.5. We say the frequency is going to guess the frequency. It's going to be the through wall times the velocity over the diameter. And then the period is just 1 over that guess frequency. We're going to say n is equal to 10. And then delta t is equal to t guess over n. And n 100. Actually, let's put 500. Sure. Now let's see what's next. Fin is going to be nn times delta t. And what else? Oh, delta t2 is 2 times delta t. Now let's go ahead and do the start time. And this is W over U plus 0.25. Okay. And we're going to define boundary layer thickness. ELP. And we're going to say it's 0.1 times diameter over the square root of Reynolds. I think that's it. Now we're just going to make a function, a step function. Location 0.1. Now let's go to geometry and start making our geometry. We have a rectangle with W, height H, position negative CX, Y, negative H2. Now let's make a circle. Equal to all the objects. Now let's do the difference here. Objects to add, objects to subtract, all objects. Now let's do our materials here. Blank material. And our density, viscosity. Now let's define the wall conditions. We're going to say these two top and bottom walls are slip condition. Now we'll go to the inlet. And we're going to say it's U times step 1 T over seconds. Over seconds. Now that's saying that the flow coming from the inlet is going to be a function of time, where it'll ramp up over time. Now let's make the outlet this wall right here. Now let's see if we can make the mesh extra fine, build it, and then instead of physics controlled, we're going to do user controlled. This is finer, extremely fine. Now we're going to go to the boundary layer, and we're going to specify the first boundary layer thickness on the surface of the cylinder. And we're going to say BLT. Okay. We're going to look at our default solver. Okay. Expand this tab. Go to time dependent solver. Time stepping. We're going to switch it from free to intermediate. So this means the solver is going to choose time steps between the time steps that we choose for our output time step. So the time step of the solver is definitely different than the time step that we're requesting as output times. So our output times are going to be 0, delta T2, time start minus delta T2, and then range time start delta T, and then we're going to do fin plus time start. Okay. Set off. Now for the plots, we can turn off generate default plots, and then we can define our own plot. Let's go to results, right click, choose plot group, right click again, do surface plot. Now for the color table, we're going to do weight classic, the range, do -1 to 1. Now for our expression, we want to do the vorticity. So let's go and find the vorticity in the z direction, multiply by the diameter, and divide by the velocity. That gives us a non-dimensional vorticity that we're going to plot. Okay. So now we've got that. Let's go to time dependent. We're gonna right click study 1 and do a parametric sweep. Let's add, we're gonna change this n variable from 1, 2, 3, 4. Actually, range 1, steps 1 all the way to 10. And then we will do 20, 25, just to see what happens. Okay. Now, let's go ahead and save this. Save as. Here, temporal resolution study. And this is temporal resolution study. Temporal. I'll do it all over. It's temporal resolution study base. Okay. Then I'll do save as, and I'll call this the run model. I have a base model and a run model. Say, now we can go ahead and run it. Look at the progress. And I'm going to go ahead and pause the recording.